Okay, students, let's continue on section 4.7, change of basis. Okay, 4.7 is on change of basis. Okay, how do we change from one basis to the other? Okay, let's say do a theorem. Okay. If and only if V is a vector space with basis V1, V2, V3, Vk. It should be Vn, sorry. Vn. Then every vector V that is in the vector space V can be written as a unique linear combination of the basis vectors. We'll just put V1, V2, Vn. Okay, so basically it's just saying, look, we can use these vectors these basis vectors to create all the other vectors in the vector space. Okay, definition. Okay, if B is equal to V1, V2 to Vn, okay, n vectors, is an ordered basis for V, and vector V is a vector in vector space V, then the scalars C1, C2, Cn is the unique n-tuple C1, C2, Cn, such that vector V is equal to C vector 1, C1 vector 1 plus C2 vector 2 plus plus Cn vector n are called components of V relative to the ordered basis B. So these scalars, let me just highlight that. Then the scalars blank, okay, are called components. Components of V relative to the ordered basis B. Okay, we denote the column vector consisting of the components of V relative to the ordered basis B by vector V in V in brackets and then base B. Okay, subscript B. That is, okay, so we denote the column vector consisting of the components of V relative to the ordered basis B. That are these scalars. Okay, we denote that by V of B, basically. V, this vector V. Okay. This vector V with respect to B, and this vector V with respect to basis B, okay, can be written as a column vector of just the scalars, the constants required to create that vector from that basis. Okay, so there's certain scalars that we would get that would create that vector from that basis. Okay. Okay, so number one, determine the component vector of V equals 1, 7 and R2 relative to the basis B equals 1, 2 and 3, 1. Okay, so they're saying that B is a basis and we can derive all other vectors, two-dimensional vectors from these two vectors, as long as we choose what the constants are correctly. Okay, so yeah, so let's just wisely choose our constants, and we should be able to get this vector V in terms of these two vectors in our basis. So I'm going to say that C1 times 1, 2 plus C2 times 3, 1, it has to equal 1, 7. Okay, and this comes from the fact that C1 V1 plus C2 V2 would have to be equal to V. Okay, from our definition. Okay, that just comes directly from the definition above. right here. Okay, so now I'm going to set up a system of equations to solve for C1 and C2. So what times vector 1 plus what times vector 2 is going to give me the resultant vector that I want, V. Okay, so I would say C1 plus 3C2 equals 1. Okay, and 2C1 plus C2 is equal to 7. Okay, and I could use substitution on this. I could put this into a system of equations, an augmented system, and RREF it if I want. However you want to solve for a 2x2. I mean, you've been probably solving 2x2s for a very long time at this point. You know, maybe eliminate a variable, however you want to do it. Okay. I'll eliminate a variable here and multiply the top by -2. Okay, so this would be -2 and then -6 and then -2, right? And so if we add that together, we're going to eliminate a variable and we would get -5C2 is equal to 5. And so C2 would be -1. Okay. Okay, and then if C2 is -1, then I know that C1 plus 3, C2 had to equal 1. So that's C1 minus 3 equals 1, add 3. And I got C2 is equal to 4. C1, sorry. C1 is equal to 4. Okay, so C1, C2, okay, would be -1. Or sorry, 4 and 1, -1. Let me write it like this. Okay, let's write it as V, vector V in terms of the basis vectors would create constants C1, C2, 4 and 1, -1. Okay. So we have vector one of the vector one basis of B basis, we'll call it vector one and vector two. Okay, in terms of the components that I would need, the constants that I would need to multiply to change that into a basis C vector. Okay. Okay. And again, if you wanted to, you could turn this into an augmented matrix and then just 7, 4, 1, 3, 2, 2, and then you could just RREF this in your calculator. Let's do that real quick, just to show how to do that. It's going to be a 2 by 3. So let's go second matrix, and then we'll do a 2 by 3 here. Okay. And coefficients that we're going to have are going to be 7, 4, 1 and 3, 2, 2. Okay. And quit out of that, and we'll just RREF it. Boom. And it shows that C1 would have to be -3, and C2 would be -5.5. Just show there. Okay, so that's a vector v1 in terms of basis C. So let's do vector v2 in terms of basis C. Okay, so let's do C1 of 7, 3 plus C2 of 4, 2 is equal to 3, 4 this time. Okay. So we'll get 7C1 plus 4C2 is equal to 3. And 3C1 plus 2C2 is equal to 4. And we'll just solve that by system of equations. It's very simple. 2 by 2 system. Okay, and so we could again multiply the bottom through by -2, -6, -4, -8. And we would end up with C1 equaling -5. And then 7 times C1 is equal to 7 times C1 plus 4C2 equals 3. So this would be 7 -5 plus 4C2 equals -3. This is -35. Okay, plus 4C2 equals -3. And then add 35. We get 4C2 is equal to 32. Right. No. 7, 4, 3. C1 is -5. Oh, this isn't -3. This is +3. Sorry about that. Okay. Okay, so this is 38. So divide by 4, and C2 is 9.5. Okay, so C1, C2, so V2 of C is equal to the column vector -5, 9.5. Okay, and so if we go back to the definition, we see that we have these column vectors. Oops. We have these column vectors, and they're just going to go side by side to create a change of basis matrix. Okay, so P as B goes to C okay, is equal to V1 of C, comma, V2 of C, okay, which is equal to, okay, -3, 5.5, -5, and 9.5. And this is my change of basis matrix. Change of basis matrix. Okay, this changes vectors that were in base B to base C. Okay, so B to C. Okay. Similarly, oops. I cannot write today. Similarly, early, messing this up. Okay, if we were to reverse this process, okay, say that we wanted C in terms of B, and find P of C in terms of B, okay, then this would be equal to -9.5, -5, 5.5, and 3. Okay, which actually is the inverse of what we got before, which is P of B to C inverse. Okay, so we can write a theorem out of that. Theorem, in general, the matrices P going from B to C and P going from C to B, okay, are inverses of each other. Okay, we can also write a theorem that states a vector in terms of C is equal to the change of basis matrix times vector V of B. Okay. Vector V in terms of basis B. Okay, so in terms of basis, the B should go on the outside. Yeah. Okay, and vector V of B is equal to the change of basis matrix B P as C goes to B times, okay, a vector in basis B is going to be equal to, we're going to take a vector in basis C and we multiply that by its change of basis matrix, and we get it in terms of basis B. Okay. Okay, let's look at an example of this. Number 4. If vector 1, 0, V is equal to vector 1, 0, find vector VB and vector VC. Oops. V in terms of C. Okay, using the bases from question number 3 and use these to show that the two identities in the previous theorem are true. Okay, so let's see the old-fashioned way. Okay, so if I have base B, which is 1, 2, 3, 4, okay, then I can say C1 times 1, 2 plus C2 times 3, 4 is going to be equal to 1, 0. I want V in terms of B. Okay, that's what I'm looking for. I'm looking for VB. Okay, so V in terms of B. Okay, my coefficient column vector. Okay, VB. Okay, is going to be equal to C1 plus 3C2 equals 1, and 2C1 plus 4C2 is equal to 0. Okay, and then solve the system however you want. I'm not gonna do the linear algebra, although you could do 1, 3, 1, 2, 4, 0, or REF it, and you get that. For me, it's faster to do the 2 by 2 by hand instead of plugging it all in my calculator. It doesn't really matter either way. Maybe it is faster to plug it into the calculator. I don't know. Never timed myself, but let's just multiply the top by -2. Okay, -2, -6, -2. This is going to give me -2C2 equals -2, and so C2 is 1. Okay, once I know that C2 is 1, I got C1 plus 3C2 is equal to 1. So 1 plus 3C2 is equal to 1. And so C2 is equal to 1. That's correct. Oh, it's C2 that's equal to 1, not C1. I'm sorry. Going too fast. C2 is equal to 1. 2 times 1 is equal to 1. And so we get -3. We're going to subtract 3. And C1 is equal to -2. Okay, so there we go. So we would say that V of that coefficient matrix, V of B, is equal to C1, -2, and 1, C2. Okay, so that's that guy. Okay, let's do the next one. Okay, so I want C1 in terms of 7, 3, plus C2 now in terms of 4, 2, because that was my basis C, right? C was equal to 7, 3, and 4, 2. And so, it's going to equal 1, 1, 0. Okay. Okay, and so we get okay, 7C1 plus 4C2 is equal to 1, and 3C1 1 plus 2C2 is equal to 0. Once again, we will multiply the bottom by -2. So -6, -4, 0. This becomes C1, 1C1, that goes away, is equal to 1. So C1 is equal to 1, and that's good. So I've got, I'll use the bottom one since it has a 0. 3C1 plus 2C2 is equal to 0. So this is 3. 3 times 1 plus 2C2 is equal to 0. Okay, subtract 3. We get 2C2 is equal to -3. And divide by 2, and we get C2 is equal to -1.5. So V of C, okay, is going to be equal to 1, -1.5. Okay, now let's verify the conversion between the basis coefficient vectors. Okay, let's check. Okay, we're going to say that V of C is equal to our change of basis matrix B to C times V of B. Okay, does this work? Okay, well, P of B to C was -3, -5, 5.5, and 9.5. And then V of B was -2, 1. Right? What's up here in black? -2, 1. So we just want to multiply these together. That's going to become -3 times -2 plus -5 times 1. That's going to be my top. That's going to be, yeah, my top component. And then my bottom component is going to be 5.5 times -2 plus 9.5 times 1. And this is going to be equal to 6 minus 5, which is 1. And this is going to be -2, that's 11. -11 plus 9.5 is -1.5, which is what V of C was. We can see that right above here. Okay, V in terms of C is -1.5. Okay, let's check the other way, the other direction. And what about V, the component vector, coefficient vector, constant vector, however you want to say it, with basis B? Okay, can I use my change of basis matrix, -9.5, whoops. P of C now goes to B. Okay, and then V of C. Okay, so we know what V of C is, it's right above us. 1 and -1.5. Can I get V of B out by using the inverse matrix of the one above here? So the inverse matrix was of that one is -9.5, -5, 5.5, and 3. Okay. I think that's right. Let me just make sure. Yeah. Yeah, that's correct. Okay, and let's multiply this out. Let's see what we get. We should get -2, 1 if we did things correctly. So -9.5 times 1 plus -5 times -1.5 okay, over 5.5 times 1 plus 3 times negative 1.5. Okay, so that's 4.5. So that should be 1 on the bottom. On the top, we're going to get 5 times negative 9.5. That's 7.5 plus 9.5 times 1. That's negative 2. And the bottom we said was 1. And so it does work. Just check. Okay. And so we can find the components of V relative to an ordered basis. Okay, the components of V relative to the basis B, or a component C relative to basis C, and then we can figure out one from the other. Okay. Okay, and that's 4.7. So I will see you in the next section.